this assessment asks us to rank the following carboxylic acids and carboxylic acid derivatives in terms of their IR stretching frequency. That is, where we would expect a band to show up in the IR for each carbonyl. We'll say that for the purposes of this, that 4 is going to be the one that would be the lowest, and 1 would be the highest wave number. Now, our approach to this problem is going to be to look at the Zwitter ion form, as we've shown up here and for each of these on the screen, and ask ourselves, how does each group that changes affect that positive charge specifically, and how tightly will that positive charge hold that negative charge? The more tightly that the positive holds the negative, the higher the stretching frequency. If it doesn't hold it tightly, we have a lower stretching frequency. And so really what we're asking here then is, how does a hydroxyl group, a chlorine, a methoxy, and an amino group impact that positive charge? And so we can go through our various electronic effects. For example, let's start with the hydroxyl group. We know that oxygen is electronegative, so it's going to pull electron density away from that positive charge to some extent. But in addition, there's a lone pair of electrons, so we can draw a resonance structure. So we're going to say that oxygen is inductively withdrawing, but resonance donating. And both of those effects are pretty good, right? Oxygen withdraws electron density by induction pretty well, but it donates by resonance pretty well. In contrast, the chlorine, once again, highly electronegative, so it's going to withdraw electron density by induction. So we'll say that, and we'll put a caps here, that it's inductively withdrawing. The chlorine also has a lone pair that can be donated by resonance, but because of the size difference of chlorine, that resonance structure is not very important. So we're going to lowercase resonance donating for that. So the net effect of chlorine is that chlorine is going to be more electron withdrawing than the hydroxyl will. When we get over to the methoxy, it's going to be pretty similar to what was happening with the hydroxyl. So we expect inductive withdrawing here and resonance donating in the same kind of way. And finally, we get to the nitrogen. Nitrogen is less electronegative than oxygen, so it's not going to be quite as inductively withdrawing. We can write that a little bit smaller for nitrogen. Not as electronegative as oxygen, so it's going to inductively withdraw to a lesser extent, but it's going to be really good at resonance, so we'll capitalize resonance donating for that one. Given this, what's the impact? Well, we would say that chlorine has a net impact of increasing the positive charge. Right? It's going to increase the positive charge on that central carbon. As a result, that's going to make this positive charge hold this negative charge more tightly. This one is going to absorb at the highest frequency. So the acid chloride, we're going to say, is number 1. On the other extreme is the nitrogen, where it's mostly a resonance donating group. Because it's going to decrease the amount of positive charge on this carbon, this lesser positive charge is going to hold this negative charge less tightly. Therefore, it will vibrate at the lowest frequency. And so we will call that one number 4. That brings us to the carboxylic acid and the ester. Remember, we said that these two effects, its electron withdrawing was pretty similar, its resonance donating was pretty similar. And so these two are going to be kind of tied at what we'll say is 2. Now that we know that these are tied at 2, we probably need to change this to being, no, it's still in 4th place. What am I thinking? 1st place, tie for 2nd. 4th place, no metal for the amide, if we're thinking that way.